Okay, we're ready. All right, today we're going to do some problem solving with the generalized Newtonian fluid, so I'm going to need your help. And let me just summarize what we did last time and see why this is the natural next step. So last time we introduced our first real, not fake, constitutive equation, the generalized Newtonian fluid. And we got this by making a guess. This is an empirical model. So we're just making a guess that it makes sense to have the stress tensor be proportional to the rate of deformation tensor. And the proportionality is going to be a scalar, but a scalar function. It's going to be a scalar function of the magnitude of the rate of deformation tensor. And we picked that so that we could because we know that in the steady shear flow material function equations, whatever is in front of the gamma dot turns out to be the prediction for the viscosity. So it might as well predict what we actually measure for viscosity. So the guess that we've made in coming up with this model has not taken into account a lot of material properties. We have that handout that I just gave you of all kinds of material properties to take into account, and we're only taking into account one material property, which is shear viscosity. But this equation calculates stress for all circumstances. It's very, very general. So the way that these things have been developed is we're going to take guesses and see how they turn out. How well do they predict all that material behavior that we've discussed? So we have all kinds of these viscosity functions. We've got the power law version of this viscosity function. We have the Kuroda-Yasuda, which is very complex. And we have this whole sheet of other viscosity functions. And each of them takes a little bit of practice in using, both for predictions of material functions and for predictions of velocity fields. So today we're going to try just the power law model, which is the simplest one and the easiest one to make calculations with. So that's what we're heading off to. And we're going to compare what we do essentially to the Newtonian case, which we've already practiced on. So we're already good at the Newtonian case. Now we'll do the non-Newtonian case. So last time I did an example. I didn't do elongational viscosity, but I did the startup of steady shearing prediction. And now we can do some simple flows that we already have done for Newtonian fluids and see how they work for non-Newtonian fluids. So this is the problem I'd like to solve with you. So as I said, I need your help because I think it's kind of boring for me to just do the problem. Instead, let's do it together. And this is the classic first problem that we did in Newtonian fluid mechanics, and now we'll do it in non-Newtonian fluid mechanics. And we'll see how all these pieces fit together. Okay, so the problem I'd like you to solve is calculate the velocity field in pressure-driven flow of a power law generalized Newtonian fluid in a tube. Steady state flow in a tube. All right? So it's steady state, it's well developed, and the tube is long. So you've been doing this for a little while, and you know that these things tell us a few things about how to simplify the momentum balance. All right? So let's do this problem together. So if we were going to do this for the Newtonian case, how would we start? Okay, so you want to start in with the constitutive equation? We can do that. So we know if we were doing the Newtonian case, we know that tau is equal to minus mu gamma dot, del V plus del V transpose. For the non-Newtonian case, we have the power law model. Tau equals m gamma dot to the n minus 1 times gamma dot. Now, if we were predicting material functions, we would know the velocity field. And we would just plug it in. That's what we did on Wednesday. But this is the other case where we don't know the velocity field, and that's what we want to solve. Does anybody remember how we would start these problems before? Excuse me? Go ahead. Continuity equation. Is that what you're saying? Yeah, we want to start with the continuity equation, which is an expression of the mass balance. And then after we simplify that, what will we do?
Momentum balance.
The momentum balance, exactly. So the momentum balance for the Newtonian, so for the Newtonian case, the continuity equation for an incompressible fluid is del dot V equals 0. What's the continuity equation for the non-Newtonian case? Same thing, right? Mass is conserved the same way. The only difference between these two materials is in their stress, which relates to the momentum, the force balance, not to mass balance. So this is the same. The coordinate system we're picking for this flow is going to be cylindrical coordinates. So we'll have to go to the book under cylindrical coordinates, and here we go. Here's an equation for del dot W, which we can copy down and use for del dot V. Okay? So I'll copy that equation. It's 1 over r d by dr of r VR plus 1 over r d by dv theta d theta plus dvz dz equals 0. So how does that simplify? So Vz changes with R, but not with Z? Well, that's true, but that's going to be the conclusion. Is there a V theta?
No.
Right? No V theta. Is there a VR? No. So this one turns out to tell us exactly what David said. dvz dz is 0. The flow does not vary in the z direction. So far, this is exactly the same as what would have happened for the Newtonian case. Okay, so for those of you who took fluid mechanics from me as an undergrad, we would always start, or last semester I should say, we would always start with this sheet. Here's the continuity equation up at the top, right? And so then we would cancel out. It's a constant density. Vr is 0, v theta is 0. We get dvz dz is 0. And then on this sheet down here, we have the momentum balance. And we have it in cylindrical, Cartesian, cylindrical, and spherical coordinates. And again, for those of you who took 3110 from me last semester, sometimes people got confused by the front of the sheet because it has taus in it. And I would point out, but maybe it wasn't always clear, this is the side of the sheet you use for non-Newtonian fluids. It works for Newtonian, but we would always use the back side of the sheet because the back side of the sheet has the momentum balance with the velocities already substituted in. Newton's law, tau equals minus mu del V plus del V transpose, has already been substituted in. That's where these equations come from. They're the same as the front, but with the Newtonian constitutive equation substituted in. So we use these equations, these Navier-Stokes equations, for Newtonian. For non-Newtonian, we can't use them because they assume this equation, and this equation is no longer true. So instead, we use the ones on the front. So this is the momentum balance And it's also in the book. On page 467, in case you want to use the book instead. But they're the same equation, so I'll use this piece of paper. Can you see them? You can't see them too well, right? Right. Okay, so let me see if this is any better. Okay. This is the equation of motion. Now, we can do this from these types of tables, which we'll eventually have to, but I'll start off by doing it in the vector tensor form so that you can see it. I know this isn't big enough. But our usual modus is exactly the same as it was when we did it for the Newtonian case. We go now to the momentum balance and start to simplify. So the momentum balance is rho dv dt plus v dot del v equals minus grad p minus del dot tau plus rho g. So we derived these a few weeks back, and now we're going to use it. We've used it for Newtonian fluids. Now we're going to use it for non-Newtonian fluids. Okay, can you help me to simplify this equation?
dv dt gone for steady state.
Right. Which one? This one, v dot del v? This is 0, why? It's a combination. This is 0 because
Well-developed, isn't it?
well-developed unidirectional flow. Yeah. This is 0 for unidirectional flow. If the flow is unidirectional, when we do this term and we go to the table, all the VR terms go out. All the V theta terms go out. dvz goes out from continuity, like David said. And then we take theta symmetry in this case. No, V theta goes out, so we don't even need that. And so everything ends up canceling out in this term. Okay, so we're going to keep all the pressure terms for now. That's always been our standard procedure. Del dot tau is not 0. And that one we're going to have to copy from the table. And rho g, what's rho g in this case? What's g in this coordinate system?
0, 0, g.
Yes, 0, 0, g. In this coordinate system where z is in the gravity direction, it's positive g. So we've got one term done. The minus grad p term, we have to look up from the table. The only special part about the cylindrical coordinates is a 1 over r term. So this is dp dr, 1 over r dp d theta, and dp dz. So that comes from the textbook also. So these two terms are identified, and we now just need del dot tau. So I'll copy del dot tau, but it's a big job. So del dot tau has 3 components, and they're the sum of various terms. So 1 over r d by dr of r tau rr plus 1 over r d by d theta of tau theta r plus d by dz of tau zr minus tau theta theta over r. So that's all the r component of del dot tau. The theta component is 1 over r squared d by dr of r squared tau r theta plus 1 over r d by d theta of tau theta theta plus d by dz of tau z theta plus tau theta r minus tau r theta. This is a term that is only non-zero when the stress tensor is asymmetric, so that one is definitely 0. That's all the theta component. And then the z component is 1 over r d by dr r tau rz plus 1 over r d by d theta tau theta z plus d by dz of tau zz. And this is del dot tau. It looks like a matrix, but it's not. It's a vector. Okay? There are a lot of terms here all added together, but each one just forms a single term. Now, really, we shouldn't really have to copy this down very often. You can download this sheet from the web if you like to use it. I will give it to you on exams for the cylindrical case. But we do need to simplify this equation now. So there's only a couple things we can simplify here easily. This term goes out because of symmetric. Tau r theta equals tau theta r. Oh, let me also point out that the structure of this is d by dr of something plus d by d theta of something plus d by dz of something. D by dr, d by d theta, d by dz. So this is the structure of del dot tau also when we did it in Einstein notation. But there are these extra terms, these crazy extra terms that are because of the different coordinate system. So that's why we absolutely have to use the handout to get here. Okay, so this is the only one we can do very easily. Maybe we could also say that there will be no theta variation. But it's really not very much. There's quite a lot of terms left over here. It's not going to turn out to be the case that we have to deal with a lot of terms. It's going to turn out to be the case that there's only one that we have to deal with. But the question is, how do we get from here to there? Where can I figure out what tau is?
Constitutive equation.
Right, from the constitutive equation. We started way back here at the beginning with the constitutive equation. This gamma dot is del V plus del V transpose. We know that VR is 0, and we know V theta is 0 for this flow. So that's going to cancel a lot of terms of del V transpose. So we're going to go now to gamma dot, calculate what gamma dot is, simplifying it as much as possible, leaving behind only the VZs that matter. Okay? Then we're going to have to calculate this magnitude. From the gamma dot we get, we're going to have to calculate this magnitude. Then we'll have tau. It will have some zeros in it. Then we'll come back here and go, oh, tau r is 0. Oh, tau this is 0. We're going to know which ones are 0. And then we can proceed with the final differential equation that we have to solve, which is not a difficult one to solve. Well, it's a little bit, it's not that hard. It's not that much different from Newtonian. Okay, so let's do that. All right, so we need to now evaluate the constitutive equation. So this is, in some sense, the extra step of non-Newtonian fluids. So the constitutive equation is tau equals m gamma dot to the n minus 1 times del V plus del V transpose. So we need del V. Del V comes from the table, and it is dvr dr, dv theta dr, dvz dr. 1 over r dv r d theta minus v theta over r. 1 over r d by d theta of v theta plus vr over r. 1 over r d by d theta of vz. dvr dz, dv theta dz, dvz dz.
You're still getting those from like page 380.
I'm getting this from page 464 in the appendix. All right, what can we simplify?
Get rid of V thetas and VRs.
V theta and VR is 0. Is Vz a function of R? Yeah. Is Vz a function of theta? No. So this is theta symmetry. Is Vz a function of Z? Why not?
Well, the
Continuity. This is a continuity equation. We got that one directly. So only one thing is staying behind. Okay? So del V is actually very simple. And then del V transpose is all zeros with this down here. So del V plus del V transpose is all zeros with this in these two positions. So let's go to that. Del V plus del V transpose is equal to 0, 0, dvz dr, 0, 0, 0, dvz dr. So actually, right now, we already know, without doing the power law part, we already know 7 values of the stress. Okay, what's tau RR? It's gamma dot times something, some number, right? Times this position, okay? So no matter what eta I put out front, no matter which of those generalized Newtonian fluid models I pick, tau RR is 0, right? Tau R theta, 0. Tau theta R, 0. Tau theta theta, tau theta z, tau z theta, tau z z. And we haven't even done very much. Okay, so actually we could go back to our stress tensor and clean it up a little bit. We know that tau RR is proportional to gamma dot, so this must be 0. Tau R theta, 0. Tau theta theta, oh, already don't care. Tau ZZ, 0. Tau RZ and tau ZR and tau RZ are not 0. So tau RZ we keep. Tau ZR, how about tau theta theta? 0 also. So just by calculating gamma dot, we've actually simplified our del dot tau to 2 terms. Oh, this one too, tau z theta, I missed that one. That one is 0. So we have a term up here, tau zr dz, and something which is tau rz dr, that are the two terms that are surviving. Okay, so that's good. We can still calculate what those taus are, though, but we have to go back and actually do the power law part. So that's back to this slide. Del V plus del V transpose, which is gamma dot, is this. And because tau is equal to minus eta gamma dot, we can conclude all tau sub ij equals 0 except tau rz and tau zr, which are equal to each other. So now we have to continue to get what eta is. Eta is, for the power law fluid, m gamma dot to the n minus 1. And here we have to remember what gamma dot is. Gamma dot is the magnitude of the tensor gamma dot, which is gamma dot over 2 quantity square root. Now maybe you can guess what this turns out to be, but there's a little subtlety here we have to pay attention to, especially in this flow. Okay? So this gamma dot is, once again, each term multiplied by itself across the diagonal. So we get 0 plus this term squared, plus 0 plus 0 plus 0 plus this term squared, so we get it again, plus 0 plus 0. And so we take that and divide it by 2 in quantity square root, and we get the gamma dot is equal to plus or minus dvz dr. Now, I've been very rigorous in saying plus or minus, but there's a good reason for it. Okay? The magnitude of a tensor is a positive number. Okay? So you might think that I should pick the positive value. Is dvzdr positive or negative? As you increase r, does the velocity increase or decrease? It decreases. Okay, so there you go. You see why I'm being careful. This velocity decreases with increasing r, and so this is a negative number. So in order for this number to be a positive number, I have to pick the negative. So there's the little tricky part about this model. Okay, the rest is just calculus. Let's see how it fits together. We now have gamma dot. We can put it in here, m gamma dot to the n minus 1. We can put this eta into the constitutive equation, and we can put in this gamma dot. So we can assemble all these pieces into the final constitutive equation. So let's do that assembly. So tau equals minus m gamma dot to the n minus 1 times gamma dot the tensor. So it's equal to minus m gamma dot dvz dr negative to the n minus 1. This is a positive number taken to a fractional power, so it better be positive. If it were a negative number, we'd get imaginary numbers. Okay, that would be bad news. Times gamma dot the tensor, 0, 0, dvz dr, 0, 0, 0, dvz dr, 0, 0. So now I can multiply this in. Notice that I have a minus sign out front. So I can put that minus sign in here. And so I've got, for tau RZ, I've got minus m times dvz dr to the n minus 1 times dvz dr to the 1. So I can make that m times dvz, this is minus, dr to the n minus 1 dvz dr to the 1. So when I have two things that I multiply, I just add their exponents and I get m minus dvz dr to the n. Okay, so this minus sign out front, I just associated it here so that I can combine these two terms. So this is tau RZ, but that's also tau ZR. They're equal to each other. So I've got tau now. Tau is all zeros except for this little expression in those two locations. So at the end of the day, tau is 0, 0, m minus dvz dr to the n, 0, 0, 0, m minus dvz dr to the n, 0, 0. So we're trying to solve for v. We're solving for v by applying the momentum balance and the mass balance. Here's our momentum balance. We have 0 equals this del p, del dot tau, which we have on another sheet now, and rho g. So let's put that all together. All right, it's going to be a little crowded. So let me write it like this for starters. It's 0 on the left-hand side equals minus dp dr minus 1 over r dp d theta minus dp dz minus del dot tau, the r component, del dot tau, the theta component, del dot tau, the z component, plus rho g, which is 0, 0 rho g. The del dot taus we have to get from our calculation. Here's our calculation for del dot tau. So del dot tau, our component is d tau z r dz. Del dot tau theta component is 0. Del dot tau 0 z component is 1 over r d by dr of r tau rz. This term is going to turn into 0 as well. Let me show you that. Del dot tau, the r component, is d by dz of tau zr. We've got tau zr here somewhere. Here it is. Tau ZR is equal to tau RZ. It's equal to m minus dVz dr to the n. So let's put that in. d by dz of m minus dVz dr to the n. Right. It's not a function of z. Vz is a function of r only, and here we're taking the z derivative of it. So this whole thing goes out as well. So that means if we go back to here, this is 0. We showed that 0. This was 0 because of all of our previous calculations, and we're left with just the last one. Del dot tau z component. Well, we can do that one the same way. Del dot tau z component, going back to our sheet here somewhere, is right there. 1 over r d by dr of r tau rz. We know what tau rz is. We just went through all this work to get it. There it is. Tau rz equals tau zr is this. So I copy that. I got 1 over r d by dr of r times this mess. M parentheses minus dVz dr quantity to the n. This is not 0. This is going to be the piece we need to work hardest on. This is the piece that goes in right here. All right, so what do we have? We have the r component tells us pressure does not vary in the r direction. The theta component tells us pressure does not vary in the theta. Exactly the same as for Newtonian fluids. The z component tells us that pressure gradient and viscous effects and gravity effects all influence the momentum balance. Okay? We do know that there is pressure in the z direction. It's given in the problem statement. So this becomes the problem to solve. Okay, so let's summarize. The r component tells us dp dr equals 0. The theta component tells us dp d theta equals 0. Z component tells us 0 equals minus dp dz minus del dot tau, 1 over r d by dr of r times m quantity minus dvz dr quantity to the n plus rho g. Not this underbar, that's incorrect. Rho g the scalar. This is the equation we have to solve for velocity. And it's not that bad. It looks worse than it is. It's really not that bad. This solves up the same way as the Newtonian case. I'm going to put the pressure and the gravity on the left-hand side. Okay, so I have dp dz minus rho g. And then I'm going to put all the viscous stuff on the right. Minus 1 over r d by dr of, I'm not going to multiply this out. I'm integrating. If I'm integrating, I rarely differentiate first. Sometimes, but not if I can help it, because it's already been factored into things that are going to make it easier for me to integrate. So I'm not going to differentiate if I'm integrating. So I'm just copying this, minus dvz dr to the n, parentheses. So just like in the Newtonian case, the left-hand side is only a function of z. The right-hand side is only a function of r. So two functions equal to the same, two functions of different independent variables equal to each other must be equal to the same constant. So this is a function of z only. This is a function of r only. And the only way those two functions can be equal to each other for all values of the independent variables is if they're equal to the same constant. So we can solve the pressure distribution and we get the same thing that we got for the Newtonian case. Okay? So I'll maybe skip that. It's very simple. Okay? But to solve the right-hand side is a little bit more difficult, but not that bad either. So the right-hand side is, I have this expression. I'm going to multiply through by minus r. And I get d by dr of a big mess equals minus lambda r. This whole big mess in here. Now actually I don't need to know what that big mess is, right? This is a differential equation I can solve. D by dr of something equals minus lambda times r. So let me define this as phi. Then this is the same equation. It says d by phi dr, I can change it to total derivatives because it's only a function of r, equals minus lambda r. And that's a differential equation we can solve. It's not even a differential equation. It's a simple integral. It's dy dx equal x. What's the integral of dy dx equal x? X squared over 2, right? So we can do this one. Let's see, sometimes I know you guys do it like this. d phi equals minus lambda r dr, integral. Okay? Left-hand side becomes phi. The right-hand side becomes minus lambda r squared over 2 plus a constant. So even though we had this big nasty mess here, because we didn't differentiate first, if we had differentiated, we would have made life hard for ourselves, but we didn't. Now we have a solution for phi, and phi now we can go back and write what it was. It was rm minus dvz dr to the n. I'm just picking that back up from this previous sheet. Phi is rm minus dvz dr to the n. So now I divide through by rm, right? And I get minus dvz dr quantity to the n equals minus lambda over 2m plus c1 over rm. Did I make a mistake? There's an r there, there's an r there, there's an m there, there's an m there. Otherwise it looks right. Now I'm solving for v. So I got to take the nth root of both sides to get rid of this n. So I'll raise this side to the 1 over n, and I'll raise this side to the 1 over n. Don't make the mistake of taking each individual term to the 1 over n. You have to raise the whole thing. Okay? If they were multiplied by each other, you could put the 1 over n in each term, but they're not. So these, you multiply them, and you get n times 1 over n, which is 1. And you get minus, and you release that minus sign, dvz dr equals this big mess. Minus lambda over 2m r plus c1 over rm to the 1 over n. Now, there's some more steps here. The missing steps are that actually back at this at this step, minus dV z dr to the n is equal to the stress. And the stress at the center is 0, so C1 is 0. I can talk about that on Monday again. So that's going to simplify this quite a bit. So this term actually turns out to be 0 by the boundary condition. And then this integration, once this is gone, is very easy. R to the 1 over n, the integral of that is 1 over n plus 1 over 1 over n plus 1. And so we end up getting something that has this 1 over n plus 1 in the R. So when the whole thing is done at the end of the day, we're very close. We get this solution that, like I said, we're very, very close to at this moment after applying the boundary conditions. The business with the rho g and the delta p, that comes from the lambda. Okay, there's the 2m in the denominator. We've got 2m in the denominator now. You can see that's there. This comes from integrating r to the 1 over n. And then this term comes from the boundary condition, the no slip at the wall. Okay? So we can quickly go through that on Monday. And then I'll also review how we did it so that you can remember what the steps are. And then we'll probably do another one as well on Monday. Okay? So enjoy the weather out there, and see you on Monday.